Hello, hello, hello. Good morning, chemist, and welcome back to another week of chem. I want to start this off by saying this will be my last week of my practicum block, and if we were in person, we'd have like a better send off and we would have got to know each other better. But still, I'd like to thank you all for coming to these lessons, sending me your work, and keeping tuned in. It's been a real pleasure to be on top of these from home, and I wish you all the best of luck in continuing your online schooling and hopefully we can get back to normal soon enough. But I'll be here all week and I'll still be around on email, so it's not a goodbye yet. But I just thought I'd let you know all that to begin. For this week, we're going to be looking at some gas laws, we call them, and these are basically relationships between different variables and gases that we will speak about and explore. This is just going to be a brief little introduction lesson for you all. Then there's going to be some reading from your book and a little practice to do. And then tomorrow I'm going to go over some more examples and you'll have an opportunity to do further practice. And yeah, I would like to remind you to get your assignments emailed in by the time you see this. It's probably already due, but make sure you keep on top of those and keep an eye out on the Google Classroom. Without further ado, I'm going to pose you all a question. Imagine you had gas just sitting in a container and you had it at a pressure of let's say 1 atmosphere. If you made the container half as big but kept all the gas inside, do you think the pressure would increase, decrease, or stay the same? This photo is kind of going over what we mean by that. Imagine you have a volume of gas and you're squishing it down. What could happen? I'm not going to tell you just yet, but if you have an idea already, that's awesome, and we're going to take that and run with it. So, that was kind of a spoiler, but see what happens here when we're this is a nice little graph being made, but we're pushing down. Look what's happening to the pressure here. Think about why that may be. We're going to explain in a second, but the image does a nice job of kind of explaining visually what's going on here. So Robert Boyle was a guy way back in the 17th century who experimented with volume and pressure at a constant temperature. Take a moment and think, why would we have to hold the temperature constant if we really want to explore the relationship between volume and pressure? Think about that. The reason is because if we change the temperature, we're already changing pressure, no matter the volume, because it's going to increase the molecule speed and the number of collisions. And that's what pressure is. Remember when we were defining pressure last week? So yeah, he plotted data as pressure versus volume. So this is saying that if you increase volume, the pressure should go up too, but he saw that wasn't really happening at all. There wasn't a constant relationship, and the line wasn't straight. It was all curved like this, which isn't what you're looking for when you're trying to establish a relationship here. So he was looking for a linear relationship, a constant and predictable connection between volume and pressure, and he didn't find it like this. But he replotted it as pressure as 1 over volume. So this is called an inverse. That's kind of a math word, but basically what this is saying is he tried to see if you increase pressure, if volume would go down instead of going up. Just mathematically that makes sense, because then if you increase this one will go down. So let's say if the pressure is increasing, you'd have a lower volume, or if you increase the volume, you'd get a lower pressure. They'd just be opposites instead of the same. And then he saw that a linear relationship emerges. And the slope is constant and predictable, and this is the basis for the relationship we're looking at, which turns into Boyle's law. We're looking at pressure times volume essentially being constant. It's not like pressure goes up and volume goes up, but the multiplication value of P and V equals constant. I think in your notes it says PV equals K, and that's K just means a constant, and that's Boyle's law. But we're going to turn that into an equation. Pressure and volume show a constant relationship when the values for volume are inverse. Cool. So this is another way of writing Boyle's law. It says that pressure is proportional to 1 over volume. So what that means is if you increase volume, pressure goes down. Look, there's the same amount of molecules in a bigger space, so they're not as confined and aren't exerting as much force on the walls. Whereas if you decrease the volume, pressure will go up. So that's what we mean by inverse. They're just going to have an opposite effect. And I will once again emphasize we're talking about a constant temperature, because as soon as you're changing the temperature, molecule movement and kinetic energy change, and that's going to affect your measurements. So we're talking at a constant temperature, let's say 20 degrees Celsius, that we're just going to see if you increase volume, pressure will go down because there'll be the same amount of molecules in a bigger space. And if you decrease volume, it would go up because, again, the same amount of molecules in a smaller space. So think about this here. We're just looking at this nice little GIF again. But what will the new volume of 40 liters of gas be if the pressure is doubled? So pressure and volume show a constant inverse relationship, and this allows for a prediction. If you'd like, pause the video for a moment here and think about what you could predict to happen. This image to the side is sort of showing a good little preview of what we're going to get at, but see if you can figure this out. So the inverse of doubled is half. If you're doubling one, you're halving the other. That's what we mean by inverse. If you're tripling one, you're making the other one a third. If you're quadrupling, you're making it a fourth. That's what we mean by inverse. So if you're going to double the pressure, you'd have to squeeze it all into 20 liters, half the volume. So you see there is a linear relationship here, like a very predictable relationship, but it's just when one goes up, the other goes down. So if pressure is reduced to a third, I just mentioned this, but see if you can remember. Right, so if pressure is reduced to a third, you need 3 times the volume. Whatever you're doing to one, you're doing like the opposite to another. If you're dividing by 3 on one side, you're going to multiply by 3 on the other. Cool. So here, pressure reduced to a third, 3 times the volume, 120 liters. Here is the equation that we're ultimately getting at. We're looking at initial conditions and final conditions. So this P1V1 means, like, you might see in your notes or other places PI-VI, and here for 2 you might see P2V2, or PS-VF for like final. But we're saying the initial are going to equal the constant. So like basically, if you make the volume bigger, the pressure is going to get lower to compensate. And if you make the volume lower, the pressure is going to get higher to compensate. So we have that P1V1 equals P2V2. The multiplication values of either side is going to be the same. And this is a mathematical equation that we can use to get lots of information about the gases we're working with, and will be the topic for like our next couple days. Take a second to write that down. It is written in your booklet too, but make sure you emphasize this equation. There we go, we got a box around it. So here's our equation, and here's a question. I'm going to invite you to try this without any prompting right now, and we're going to go over it in about 5 or 10 seconds, but just try to set up your variables. Identify what needs to go where, plug them in, and see if you can get a value that makes sense, given what we know about the relationship between pressure and volume, in that when pressure goes up, volume goes down. So let's read this carefully. It says if 3 liters of gas is initially at a pressure of 1 atmosphere, what will the new pressure required for a volume of 0.5 liters? So we're going down by 6 times in volume, so think about what that could do to pressure. Take a second to predict. So we have a starting pressure of 1 atmosphere, initially at a pressure of 1 atmosphere. We have a starting volume of 3 liters initially. And the new pressure is going to be at 0.5 liters, so that's our second volume. So then we can make sure that we have the same units and the same, like, everything. That is one thing that you're going to have to note here, and one place that does become tricky. Make sure you always have, like, liters and liters, or the same pressures, and not, like, a mix of milliliters and liters, or a mix of atmospheres and kilopascals or something. You have to have the same units on either side, and that's, like, the one big asterisk to this, so just make sure that's something you're always checking. But yeah, here we're going to go 1 times 3 equals P2 times 0.5. Just going to divide that. And 6 atmosphere equals P2. So decreasing the volume to 1/6 will require a 6 times pressure increase to 6 atm. Cool. Take a second to pause this and copy this down in your notes if you're writing, which I suggest you do. And yeah. Same type of example here, but just kind of reversed a little. I invite you to pause the video and try to solve this one, and we'll go over it in a moment as well. Alright, so A syringe contains 20 milliliters of a gas at 100 kilopascals. The pressure in the syringe is changed to 25 kilopascals. What is the new volume of the gas? So here notice that we're decreasing the pressure by 4 times. So think about what that might do to volume. Take a prediction. So again, our P1 is 100 kilopascals, our V1 is 20 milliliters, our P2 is 25 kilopascals, and we're looking for V2. We're going to use the same equation. This is the Boyle's law equation. And we're going to plug in all our known values and then solve for V2. I'm going to do another little divide thing here as those move over. And we get 100 times 20 divided by 25, which equals 80 milliliters. So decreasing the pressure by 4 times, or like to a quarter, will cause a 4 times increase in volume to 80 milliliters. This is what we mean by inverse proportionality. All right, I think that's all we have to show for this little lesson. The main thing with this unit is to do practice, and just do lots of practice. So I'm going to give you some practice for today, and I'm going to give you some notes to read, and then we'll have even further practice tomorrow. And once we're all practiced up, then we'll be good to move on. But this is a topic that requires a lot of doing. So I hope you all have your calculators handy and feel like working through some of these, because that's going to be the focus. So pay attention to the Google Classroom post and see what you're meant to do today. And again, email me mrbsciencemp@gmail.com with any and all questions, and I'm happy to help. Hope you all have a lovely day, chemists. Thank you.